So, as I said, welcome everybody to Applications of AI in Manufacturing with Festo, part of the AI for EAC Innovation Challenge. In terms of etiquette and hygiene on the call, I'd ask you to all remain on mute if at all possible. There will be a chance to ask questions. You're, of course, welcome to ask questions through the chat function. And we will hear now from our partners at Festo, Dr. Imani and Dr. Schubert. And we're very happy to hand over first to Dr. Imani for some words of welcome. Over to you, Dr. Imani.
Yes, thank you, Paul, and very warm welcome to all the participants and the students and partners from the East African community, and also a pleasure really to open today's webinar on artificial intelligence in manufacturing. So basically, we are living in a very moment of profound transformations around the world. So we all know that manufacturing stands for a true value-added creation and also therefore job creation. And that's really helped us entering a new era where really data and intelligence are just as important as the machines and technologies that we were using in manufacturing. So here we are, artificial intelligence in manufacturing becomes so important. And the question is, what does that mean? And what is exactly all about? So it is not really a distant concept. It is already part of the so-called smart manufacturing. And today's webinar will be an introduction to all of you, also from Festo, to really have a kind of window of demystifications of terminology that we are using in artificial intelligence in manufacturing. So today, we are going to explore over the next couple of minutes, probably 90 minutes, but we would like to reserve also some time for question and answer, so that we will really go through the core building of according blocks of the artificial intelligence. And also that will bring us a kind of simple best practice overview of the AI in manufacturing. So we will grasp let's say, clarity on essential terminology like artificial intelligence in machine learning and deep learning, so that this concept will be considered as tools that can be used very much so rather than the buzzwords that sometimes create confusions. So we will also learn about Festo Didactic, how we are integrating AI in learning systems and industrial training basically worldwide. So learning system for education and also continuing education for the factories, for the industries, lifelong learning. Festo has a deep roots in advancing technical education, and we are really much committed supporting the development of the industry in East Africa, where really innovation and youth potentials will be foundational for the industrialization of the economy in this part of the world. You will further explore also in this webinar the machine learning based quality inspections. So that's also very important in terms of gaining accuracy, consistency, and speed in the industrial production. So that will address some concrete large language models in production environments. And that will also show us how it's possible to improve maintenance, workflow automation, and also decision-making in production engineering. And finally, you will get introduction to the Festo automation experience. That's our AI-based solution that turns industrial processes data into actionable insight for smart maintenance and improve machine performance for a higher, better OEE, so overall equipment efficiency. That will help us to reduce downtimes of the machines and production. That will help us to increase the efficiency of our production facility, and that will also support sustainable manufacturing in terms of environmental friendly manufacturing, use of better energy management, but also material use and so on. So through today's sessions, I really encourage you to come up with your questions together with Paul Kennedy, my counterpart from Zindi. We will be trying to address your questions, but also the assumptions that you will have, challenging theses that it will be given through this webinar. For sure, we will try to address them as much as we can during the live sessions. But in case that we will not be able to cope with your raising questions and comments and assumptions, for sure we will address them one by one, and we will be sending and sharing this in a written protocol after the sessions to all of you. So concluding, I want to emphasize that the future of artificial intelligence manufacturing is not really happening somewhere else. It is happening at your site. So that's so important. So East Africa has the talent, the universities for that, the entrepreneurial spirit, and the growing industrial base to become a leader in smart manufacturing landscape. So this is already a true reality within the grasp. So thank you once more to really joining us for these sessions, these webinars. This is, and I hope it will be a first step towards a long-lasting partnership with universities and the academia in EAC. So it will inspire you to explore new possibilities and to see yourselves as an active shapers of the next industrial area of Africa. So thank you so much. And I would like to hand over to my colleague, Dr. Tobias Schubert, who is an expert in artificial intelligence, and we will be also exploring together with him through the materials that he has been presenting. So I would like to say, Tobias, maybe over to you. Thank you.
Thank you very much, Nader. Hello to everyone. Thanks for inviting me. Thanks for the introduction. So let me share my screen. Let's go to this one. Okay, could you see my screen?
Not yet.
Oh, not yet, really?
So it seems that others can see your screen. So others, they can see your screen. Fantastic. I cannot, but it's okay.
Okay, really? But the others can see my screen.
Yeah, it seems that it's okay. So just move on.
Okay. Yeah, I will give you a short introduction to artificial intelligence might mean in smart manufacturing, and what we do, like Nara said, at Festo Didactic. So the outline, I would start with some basic terms and definitions, because I think it's quite important to know that there is a difference between artificial intelligence and machine learning or deep learning. I will then show you, let's say, the most prominent applications that at least we can found in Germany, ML and AI in manufacturing. I will give you some rough ideas what we do at Festo Didactic, just to put what we see in industry to educational purposes. And finally, I want to speak a bit about generative AI, as you know, Gemini, Copilot, ChatGPT, and how this will, at least from my point of view, will change our way of communicating with machines in production lines. So basic terms and definitions. So quite often what you can see, at least in newspapers, for a lot of people, journalists and so on, AI and machine learning is completely the same. But from a computer science perspective, it's completely different subdisciplines. So if we talk as a computer scientist about artificial intelligence, we really mean all techniques that allow computers to somehow adapt human behavior. That's one definition. But to artificial intelligence, there's also knowledge representation, the entire game theory is also part of artificial intelligence. So it's really a huge domain where computer scientists do a lot of research. One subdiscipline is machine learning, and it's here the key point is that we try to enable computers to extract knowledge, maybe new knowledge or hidden knowledge, and relationships based on training data. So the key point here is in machine learning, we as a domain experts provide training data to a machine learning algorithm, and the machine learning algorithm tries to find out what's given in that data. So typically it's not possible for the machine learning to extract completely new science or new data or new insights, but just to extract them that are already given in the training data that human people provide to the machine learning algorithm. Now, so the machine learning algorithm will never be what you read sometimes in newspapers, an AGI, an artificial generic intelligence. And the most important point, at least in nowadays, is deep learning, because that's machine learning. Machine learning can also be decision trees or just an if-then-else statement, if that's enough for your application. But deep learning is just using neural nets as the underlying algorithmic basic. And if you take a look at all these efforts that we have achieved in the last, let's say, 10 to 20 years, most of these success stories belong to the field of deep learning. So they are based on neural nets. They are based on a lot of data, a lot of good data, a lot of training, a lot of graphic cards. But it's deep learning. So if you are computer science, you would say it's deep learning and not artificial intelligence, just to make that clear, at least from my point of view. Yeah, and of course, one could ask, why is deep learning so popular nowadays? So the entire story of neural nets and perceptrons and all that stuff was invented in the early 1950s by Weizenbaum. Then let's say the AI winter happened. Nothing happened until, let's say, 1995 or something like that. But now it's everywhere. One benefit, of course, is you do not have to write computer programs anymore. So if you want to, just a sec, laser pointer. If you have some data as an input and you want to map it to an output, in the good old days, you're just programming a program, mapping these input data to the output data. Instead of doing this, you maybe have some input data, you know how the output should look like, and you take these two vectors or sets of vectors, train a neural net or a machine learning algorithm in general, and you will end up with, let's say, a program, a trained model that does the same, mapping your input data to your output data. So it's no longer programming in a sense, but it's more like training models for a specific task. The second point why it's so popular nowadays is because of the huge power that graphic cards provide. Right? For example, since NVIDIA opened its CUDA platform for AI development, that was a breakthrough, and that was 23 years ago. So we now have computing power that can help us to solve complex tasks, even such tasks where we have no idea how a program should look like, or we even have no idea how the mathematical formula would look like. Just give a lot of input data to the neural net, which is running on the graphics card, train the model, and it's surprisingly good, as we can see by ChatGPT or the Gen AI algorithms. And in many cases, that's another really benefit that should be pointed out, at least from my point of view. You can reuse your basic structure. So if you, for example, have a framework for identifying dogs and cats, you can use the same framework to distinguish between cars and planes or whatever. Just take new data, train it again, and you have a complete new application scenario. And another point is what one also should know is that we have three major strategies, which are called supervised, unsupervised, and reinforcement learning. And depending on your application, one of these three strategies fits best, and often is really the first choice you should take, helping you to successfully implement machine learning or AI, if you want to call it AI. Maybe some words about these different strategies. So supervised learning, I guess everyone knows supervised learning. So typically you have labeled data. You have images from your dog, images from your cat, and you know that's a cat, that's a dog. And in supervised learning, you just take the input data, the images for your neural net, let the neural net analyze what happens, give you some result, and that label at the end should be a dog if the input image is a dog. So you have a target actual comparison during training, and that massively helps in training neural nets. So that's really the state of the art if we talk about image processing with machine learning. Of course, labeling thousands of images is really a time-consuming, boring, sometimes frustrating job. So if you think about an everyday example, it's like learning with flashcards at the university or school or whatever. So assume you have one of these cards and you have an image, let's say, of a particular type of rock. Then on the back-end side, you know the technical term. So whenever you try to estimate which kind of rock that is, you can switch the flashcard and directly see the correct solution. So that's what labeling means in that terminology. Typically used for every kind of image processing with machine learning. So another part is, let's say, unsupervised learning. They typically have no labeled data. You just have data. And what the system tries to do is it tries to sort the data, the different data points or vectors in different buckets or bins. In bins where the data points have some similarity. And during regular operation, for each input that you have, you try to find that bucket or group or bin where all the objects that are located in that bin have some kind of similar properties. I guess you know that from online stores or streaming services. So customers who bought item X are also interested in item Y, or customers that love a particular Netflix movie might also love another kind of particular Netflix movie. That's all unsupervised. So if you think about an everyday example, it's like arranging books on a shelf. You can do it by the color or by the theme or by the authors or whatever. Whenever one is asking for a particular, let's say, kind of book, like a documentary or something like that, you go to the shelf of the documentaries and grab one. So that's unsupervised learning, which, for example, we use for our Festo AX system. Reinforcement learning is typically used for robots or robotics in general. What we have seen before was supervised and unsupervised. You have an input, you get directly an output. Reinforcement learning is tackling all that application scenarios where we have a number of actions, and only after a number of actions we will get a result. So for example, chess computers, it's a huge example. So you have to play some moves until you know you made it or you've lost. And the idea is not to come up with a chess computer by programming, but let the system on its own determine what are the best moves, what are good moves, what are bad moves. So it's like a trial and error. It's like when we do, I don't know, learning to walk as childs. We do some steps, fall to the side. No, okay, that was not a good idea. Let's do some other kind of steps. It's just that way. It's typically used for robotics. Another everyday example would be how to race a car around a circuit. So you race one lap and you get your lap time, but you have no idea how to improve your lap time. So you're doing it over and over and over again. And at the end, you might know, in corner 2, I have to slow down because then I have to speed. Can I speed up in corner 3? And at the end, I have a faster lap time. So it's always step by step by step by step, and a total reward, positive or negative at the end. So that's the idea. These are the 3 strategies that are used over and over again in AI and machine learning. Just to set the stage, maybe some examples of where we find manufacturing, at least from the industries I know in Germany. What we see over and over again is optical quality inspections. That's more or less standard or default since, I don't know, decades. Now it's, of course, it's using machine learning. Now it's using AI. And the idea, of course, is before shipping your products to the customers, you want to ensure that your product is fine. So faulty products should not be shipped to your customers. So you have to detect whether your part is okay, or if it's faulty, move it away. And by using AI, as I said before, you can quickly adapt it to new work pieces. It's not reprogramming anything. It's just giving new training data to the system, train the neural net, and you are fine. And of course, you can run it at a high speed throughput. No one is getting tired. Different lighting conditions and perspectives typically are not an issue. You just train it once and then you are fine. It will work forever. And you can also use machine learning based results to automatically add data to your database just to provide information of your product, or just to show that something is going down over time. More and more products are getting faulty, which might also give you a hint that something in your process is not working fine anymore. So that's very, very typical application scenario, which we can see over and over in industry. The good old days done by classical detection mechanisms, nowadays typically done with machine learning, sometimes even the machine learning also integrated in the camera system itself without any supercomputer being located somewhere. The second part is predictive or smart maintenance, and I guess that will be really a game changer in the next coming years. So what we typically have, we have a lot of data coming from our machines. Temperature, humidity, I don't know, active power, airflow, whatever. We can summarize all of them. And then we can use some kind of machine learning just to analyze what the data is representing. Is there something that is going into the wrong direction? Is there more power required? Do we have a leakage? Do we have more friction on the conveyor belt and all that stuff? So that's what we call smart maintenance. We have that implemented in one of our, what we call the technology plants. And we are observing about 550 systems with such kind of a smart maintenance system. So the idea is always the same: avoid unplanned downtime. Now, if you go for a car manufacturer, which is also using Festo X, for example, they want to avoid downtimes, unplanned downtimes. So they are observing 4,500 welding guns for their car production. And once that system is going down for 1 minute, it's 10,000 of euros. So they want to avoid that. And systems that can show you, oh, there something is going in the wrong direction, please send a maintenance guy to production line 1 or 2 or machine number 3 and check if we have to replace some parts or something like that. Is really a game changer in the industry right now. I will come back to that later. Another example for that smart maintenance is by ThyssenKrupp, which is a German company who is building elevators around the world. And what they also want to avoid is that their elevators are not working anymore. So what they do is they collect sensor data from all their elevators all around the world, analyze this, try to find anomalies, send a maintenance guy to a particular elevator before the elevator is crashing or is going out of business and it's not working anymore. What we also see is robotics, and again, I would say in particular cobots, where humans and robots collaborate without protective fences or something like that. That will be also a game changer in the future. Yeah, just to let the robot do the simple stuff and let him work together with the worker. That I guess that will be a game changer in the future as well. Maybe even with humanoid robots. That might be also interesting. And what we can do here, that's an example of what we did at Festo Didactic. We took some of these cobots, so no fences, no separation. We put a camera on top just to see what's going on in the scenery and said the robot, whenever somebody, like me, it's my hand, places a workpiece, please grab it and put it somewhere else. So is it the wrong medium? Okay, here it's the other way around. He's taking a workpiece and placing into my hand, but the other way works as well. So it's so the key point is you have a camera system which identifies and localizes your hand and puts the workpiece into your hand. Here it comes. That's the other way around. So of course you need a 3D camera system to guide the robot where to go and then grab or place the workpiece. Here are some more examples also from Festo. So one of these examples, I guess I like it. It's called the bionic soft hand. And the idea is it should learn how to manipulate the cube's position in the hand. And that's typically a reinforcement learning stuff. So we have a simulation. So each of these simulated agents is trying to learn how to manipulate the cube just to end up with a black surface on top. Yeah, so the idea is you do not program that bionic soft hand. You just take a digital twin, a simulation, and in that simulation you define what is the initial position of your hand and the cube. How does your environment look like? What does it mean if you move your fingers and you say, okay, the goal at the end is to have the black surface on top. And then you let the system run for hours, 2 hours, 3 hours, 5 hours, depending on GPU power. And finally, the system has learned how to come from the initial state to the goal state. And then you can take this plan and put it on the real bionic soft hand or on the real robot, and it will behave completely identical. Here's another example. Here the idea was this chair has to be colored, and the cobot initially had no idea how to do that. It was just defined in the simulation. That's your starting point. You're here to color that desk, that chair. Please try to learn what that means. It took 8 hours or something like that to come up with a solution. But since the simulation was so close to the real world, what they did in research at Festo, they took the identical cobot, they took a chair, and they did it in reality, and it worked perfectly fine. So that's how you typically use reinforcement learning. You take a high-speed simulation just to learn the plan, and then put it into real life. And I guess robotics, reinforcement learning, large language models, interaction between humans and cobot, that will be a game changer in the next years from my point of view. Of course, process and business optimization. Here's let's say, maybe it's a funny example, but I like it. It's from an online shop in Germany, Zalando. And the idea is they have a logistics warehouse where they have all their orders, all their products that can be ordered by customers. And then they analyze the orders by the customers. just to get to know which parts are typically ordered together. So maybe shoes and trousers or whatever. And the idea is to put these products, which are often ordered together, into one of these logistics zones. Just to ensure that the worker which has to grab the shoes and the trousers has a very, very short way to go, because that optimizes the time the worker has to stay in the logistic warehouse, and that also speeds up process and increases throughput. So that's a very simple example how to arrange your warehouse by using AI and analyzing which orders typically contain the same type of product. Another optimization, it's almost 10 years old right now, but at that time it was super impressive. DeepMind was an AI company. Now it's part of Google, and they reduced the cooling bill at one of these data centers of Google by about 40%, which is a huge number, which is really, really a huge number. And what they did is they analyzed the current CPU consumption usage. They also analyzed which kind of GPU and CPU performance they will need in 1 hour, in 2 hours, what has been scheduled for tomorrow. And then they put their cooling systems appropriate according to what they estimated they will need tomorrow or the day after. And by doing so, that really, it's almost half of the cost. So that's a huge, huge point. What we see right now, since let's say 1, 2, 3 years, some kind of support system. So they are typically called the AI co-pilots that we have. So we have it in Siemens PLCs. We have it in some robot vendors like Fruitcore, for example, which are producing a robot which is called Horst. So once you want to program this robot, you can ask the co-pilot, how can I do that? How can I teach a position? Can you provide me some templates? Can you program this part and all that stuff? So that's the typical AI co-pilot based on large language models, as we can see it in a lot of different fashions right now. But it's also coming more and more, and we also have something like that for our learning factories, for example. I will show you later. Okay, so these are the typical, some of the typical application scenarios where you can find AI and ML, at least in Germany nowadays. And what we do at Festo Didactic, because we are focusing on education, we are focusing on application scenarios in which students can learn something about machine learning, where they can do their own experiments, where they can fail, but where they can also have success. We try to map some of these industrial applications to what we call the learning factories, for example. So our aim is to empower today's and tomorrow's skilled workers, okay, blah, blah, blah. Besides other products in our portfolio, we also offer what we call the learning factories, smaller one and the larger one where I typically am working on. And the idea is to have on a small scale a production line having all that different topics which you might also see in industry, like a car manufacturer or I don't know. So our learning content also deals with Industry 4.0 aspects like RFID sensors and writers, manufacturing execution systems, PLCs, of course, sensors, actuators, and all that stuff. But of course, also some kind of machine learning and AI. And that's what I want to tell you in the next minutes. So what is typically happening in our learning factory? So the default product that we are producing, it's not really a production, but let's say it's a simulated production. So first of all, what you can see, we have a conveyor belt So all the products are somehow transported over that entire line, maybe are processed in a CNC machine, maybe we have a robot assembly, we have some kind of our own logistics warehouse, we have some additional application modules, maybe a manual working place. But in general, what happens is we start with an empty pallet. That's the one that is going around the conveyor belts. Typically, we put a front cover on top of the pallet, maybe inserting some kind of fake PCB. The robot assembly is mounting some fuses, which is the application module over here. We put a back cover on top. Maybe we also have labeling, pressing, turning, heating. And finally, what we have is a final product like the one here. You can see it as a, let's say, as a cell phone. Yeah, so we have some kind of a fake display area. We have a fake area for a camera system or something like that. So we are not producing real stuff that will be shipped to customers. It's more for the education domain. So as I said, we have a cell phone production, and what we also typically focus is a customer-specific production in batch size 1. That's a very famous idea of Industry 4.0. So we can also have some variety with respect to the color of the front cover, back cover, how many fuses, do we need a PCB, yes and no, all that stuff. So that is what typically happens in our learning. And if you now think about the optical quality inspection that we had early in this presentation, we can also add this one to a learning factory. Yeah, so we have a camera over here. And once we have the camera, we can check a lot of different stuff. Now, we can do some target actual comparisons. We can check for labels or colors, dimensions, and we also can check for damages or objects that should not be there. So on a small scale, we can do the same optical quality inspection that is done in industry nowadays. And we did it by coming up with our own machine learning algorithm, which is implemented completely in Python. Here's one of the examples. You can have a lot of different parameters concerning the camera system that is integrated. But what we typically do is we first of all identify everything that we see. So for example, we have a front cover in blue, we have a PCB, we have a fuse over here, which is at the same time the front fuse because the rear fuse is not mounted. Here we also have some kind of an printed circuit board tests. So typically if you have lines on a circuit board, they should not interact with each other, which is a defect. They should not be interrupted, which is a defect. And a scenario like this one would say, okay, that part is faulty, and faulty means it has to be replaced from the line. Yeah, this is one example, just to show it live from a trade fair. So that's a camera system that we have. It's an industrial one. Here's a workpiece. Sometimes we simulate scratches with a chalk marker, just to not destroy our workpiece, but just to show what's going on. Okay, so the workpiece is going to the camera system. It is making an image, as you have seen by the flash. And it has detected the scratch. So typically a scratch is another idea. If it's a small scratch like the one that we have here, okay, let's go to the manual working place and do some polishing, and then everything's fine. If it's a larger damage, it will be replaced from our system as well. So that's the idea. So what you can see in industry put into a small scale for our learning factories. Here another example, very simple one. So that's what we call the skills conveyor. It's just a conveyor belt going from left to right. We have a small camera system over here, and the idea is that camera system is checking pizzas. So in Germany, pizzas are very, very important. And if you take a look at salami pizzas, they should have enough slices of salami, of course. That's another example what students can learn, can program, can do, because that system over here is connected directly to that simulated PLC program, and then they could learn how to program the conveyor belt. So if the salami is fine, then it should go to the right-hand side. If it's not okay, then it should go to the left-hand side. So these are the smaller examples which are also fall in the optical quality inspection stuff. Another point is that human-robot collaboration, as we already saw, and I would say it will be a game changer in the future. So maybe it's a good idea to allow students to get familiar with that basic concepts of robotics, of image processing, because we always need a camera and the combination of both of them. Now, as you can see, we have different application scenarios, different setups. For example, here is one use case where you can push the robot from the right or from the left just to determine which kind of colored suite you want to have. Then you put your hand somewhere over there and you get your suites. The application scenario, what we are doing is always, it's very simple because it's an educational one. So what we have on top a 3D camera that is continuously generating a video stream that is sent to a machine learning PC, where again we have a Python script who is doing all that analysis and is also controlling the cobot. So we have some kind of an object detection to identify objects or human hands and to direct the cobot. So the first step is always something has to be grabbed. So we need the object detection to grab, for example, an SD card. Second step is always put something in the hand. Okay. And then we are done. So that's what we tackle right here. And for all of those of you who are familiar with robotics, of course, you know, okay, what is a tricky point at that scenario? It's what we call hand-eye calibration. Because the 3D camera, which is on top, has its origin of the coordinate system somewhere on top, while the cobot has its origin of its coordinate system here at the base. So you have to do some kind of a translation between these two coordinate systems. And what we did is we keep it simple. Let's do it again with machine learning. So what we did is we take a special marker, which can be detected by the camera quite well. And then we say the robot should drive to, let's say, 100, 200 positions. Now, somewhere over here in his working area. And once he has reached a position, he will stop. The camera will make an image and will analyze the position of this marker. What you then have is you have, let's say, 100, 200 cobot positions and the appropriate, let's say, marker positions from the camera. And then you can just do that mapping from one to the other. Now, so you can do a mapping from the camera positions to the robot positions with some kind of a regression machine learning algorithm, which is not that complicated, just to approximate the function. Whenever the camera says the human hand is over here, what does this mean in robot coordinates, where the robot should go? So X prime, Y prime, Z prime, for example. So that's the most tricky point. Of course, you can think about a lot of additional future work, and that's an example, Gripper AI from research at Festo, which is already used in industry. So here the idea is, maybe let's go back to this one. So typically what we have is a vacuum gripper, or we have a parallel gripper. But sometimes you need a vacuum gripper for one part, but a parallel gripper for the next part. You don't want to unmount the parallel gripper and manually mount the vacuum gripper. So it would be a good idea to have different tools or grippers at the robot and just to select which one is the best for a particular use case. So maybe here the camera, it's a 3D camera over here. We recorded an image and said, okay, it's a solid workpiece. there we take the parallel gripper. It's an inter-real sense 3D camera, which is over here. Next example, just shooting an image. It says, oh, it's not a solid, it's like flexible, so let's take the vacuum gripper. And that's an interesting use case because you can switch the gripper without any human interaction. That's really interesting. And of course, let's go back. Another idea, and I will come to this later again, is to combine a cobot with a large language model just to control the cobot just by text, for example. Okay. The next topic that we tackle, and as I said before, it's smart maintenance stuff. So, which is called in our company Festo AX, for automation experience. And the idea is to have an easy-to-use solution that enables you to use machine learning, to get data and information about your systems in order, for example, to go for predictive maintenance. So the idea is detect anomalies before they really matter. Now, like I said before, if you monitor 4,500 welding guns and you want to avoid downtime, you check 4,500 welding guns, whether they behave like yesterday or the week before, or whether they behave like an optimal welding gun. And whenever there's a difference, okay, let's send a maintenance guy to that welding gun and let's check if we have to replace something before it comes to an unplanned downtime, or if everything's fine and the system will work for another 2 weeks. So it's just to help the maintenance group to focus really on that systems that might have an issue. Not checking everything now and then, but just focusing on the ones that might cause trouble. You can do the same for predictive energy. So leakage is a huge problem in industry. Leakage really costs money over and over again. So you want to have some kind of an energy monitoring with respect to your pressed air, just to detect leakages as early as possible, just to avoid throwing money out of the company. We try to do this also and our didactic systems, and I wanted to show you a live demo, but the network has some issues today, so that I unfortunately have to skip that. But the idea behind Festo X is, if you take a look at an asset, so an asset might be a cylinder, for example. Now, cylinder is moving for back and forth and so on, takes some time. So maybe the cylinder works well for, let's say, 2 years, 5 years, 3 years, and then it somehow is getting worse. So maybe the cylinder is not moving that fast again as before. It's going slower and slower and slower, and at the end, it might crash. It might not move anymore. So, and then what do we do typically in manufacturing? So in the good old days, we had that typical kind of preventive maintenance. So based on fixed intervals, we say, okay, let's replace the cylinder every 24 months. That might be too late, but it might be also far too early. Which costs money you don't want to spend if the cylinder will work for another 23 months or something. So that's not the very best you can do. Let's assume the degradation starts over here. So it's getting worse, but really on a very, very small scale. And maybe you have a condition-based maintenance, which is a bit better than the preventive. So you just have a threshold. Now, concerning your cylinder, if it's going back and forth, you say, okay, if it takes more than 200 milliseconds, something is not okay anymore. Might be okay before the failure really happens, but it might be also too late. because sometimes the travel times of a cylinder is not linear, but it's an exponential curve, and then it might be too late. Maybe you have a dashboard, which we can see in a lot of industries. So there's a dashboard, how the cylinder behaves. The expert take a look every morning or every afternoon. And then based on their experience, it can say, okay, I guess something's going wrong. But it might be also too late. So the idea of Festo AX is once the degradation starts, shortly after that, I want to see an anomaly in AX. It should show me something is not okay anymore. And it's not that important to say when it will fail. That's not the point. That's from a mathematical point of view, very, very hard to achieve. But the idea is to have that kind of a human closed loop. Yeah, so your system says quite early, something is going wrong. And then the expert says, okay, looks pretty like that we have an anomaly. Let's send a maintenance guy to this machine. So in the welding gun example, if you have 4,500 welding guns, and one is sending such signal of an anomaly, you will just focus on that single welding gun. If none of the 4,499 other welding guns show something like that, you don't care about them. You don't have to take a look at them. Just focus on the ones where you see something is different. Yeah, from a high level point of view, it's an anomaly detector. It's unsupervised learning, as we have seen early in this presentation. And the idea is focus on data coming from a fault-free production system. Now, so it just means we do not collect data from faulty behavior or something like that. We just put that welding gun in place. We take a look, is it okay? Then we let the welding gun do its stuff 1,000, 2,000, 5,000 times. We take all that data, and based on that data, we train a clustering algorithm. A clustering algorithm, here the idea was to put all these incoming data in groups that somehow have similarities. So maybe your welding gun, or the data of your correct welding gun results in 3 different buckets, the red one, the green one, the blue one, because sometimes you have to weld some other kind of steel or whatever, I don't know. So these are the buckets that you have, and since you have trained it only on good data, every data point that is over here or over there or in the green area will be a good data point. Then you know everything is completely fine. So what you do in real deployment after that is you take your live data, put it to your trained clustering algorithm, and predict the health state of that component or monitored asset or welding gun or cylinder or pressed air or whatever. And if the system under consideration or your cylinder, your welding gun works as expected, the live data that is coming will fall into one of these buckets. And then you know, okay, everything what is inside these buckets is good data. System works fault-free. We are fine. Now, so that's some example from our learning factories where we have a magazine cylinder going up and down. And then you know, okay, everything works fine, 99% health score. I don't have to take care about that. No one has to go there. That cylinder is working fine, or that welding gun is working fine. If on the other side, it changes its behavior, so it's getting worse, until that live data point is not fitting to any of these buckets anymore, then you know, okay, something's gone wrong. Something is behaving different from what I've expected. I've trained it in a fault-free situation. I have 3 fault-free buckets. That data point is not fitting anymore to one of these buckets, and I know something is different. And then it's a good idea to send your maintenance guy to explicitly this particular cylinder, welding gun, or magazine in our factory. You don't have to focus on all the ones where you have 99%. Just focus on the one where it looks like you have an anomaly. And that really reduces downtime, of course. It reduces costs and effort with respect to maintenance. And that's really a huge help. So, as I said, unfortunately, just take a look at that, but it's still not connected. We have some network issues today, so I wanted to give you a short live demo, but maybe we have to postpone that. Final aspect where I also think that will be definitely a game changer. The future is generative AI. So yeah, I guess we all know that. Yeah, so the prominent members of that kind of machine learning or artificial intelligence are Microsoft's Copilot, OpenAI, ChatGPT, Gemini, Claude, and all that stuff. Yeah, so generative AI in general means you have some kind of a system which learns from patterns and can use its patterns to create new content. Like you can see over here, that's just a summary of what is provided to every Festo employee. We have a Gen AI which can help you answering emails. You can have the speech to text, you have text to speech, you can have a text to image generation. And that's all. These are the typical members that you all see in ChatGPT or behind ChatGPT, behind Gemini, and all that stuff. But these well-known use cases, of course, are not directly connected to manufacturing. So generating an image from text has no relationship to production, I would say. But there are many use cases. So for example, generative design is one. So maybe let's think about the next generation of production machines. Why not asking a large language model, how should it look like? Maybe supply chain management, predictive maintenance, of course, is an issue. Training simulations, that's more like the education stuff. Energy optimization. There are a lot of different use cases, and there will be far more in the future, I would say. And I guess one game changer, of course, is again with cobots, robots in general, because you can, if you have a connection between a large language model and your cobot, you no longer have to be a robot expert. You just tell him what he should do. Here's one example. So please remove any waste you can find in the bin. Okay, I will do that. So that will definitely change the future. As I said before, that Copilot-based support systems that are widely used right now, I would say, so Siemens PLCs, there's an entire ecosystem which helps you in programming Siemens PLCs. It's based, that's important, it's based on OpenAI service in the cloud. So it's not locally on your machine where you have your tier portal, but it's using a cloud-based system. That's a startup coming from Germany as well. That is really interesting. They are also using Gen AI combined with a lot of different things. So they have the 3D object detection, like we also had in our cobot system. So you can localize a screwdriver. They have a camera system. They have speech control, gesture control. And they have some kind of a vision language action approach. And that's really interesting because what you say is, please give me the screwdriver. So what the system has to do, first, it takes an image. Where's the screwdriver? Do I have a screwdriver? That's based on what I told the system what it should do, and then it should make a plan. Okay, the screwdriver's over there. What should I do? How to move the robot to that place, how to grab the screwdriver, where's the human, how to go to the human, how to give him a screwdriver. So it's a very complicated system, but that's an interesting research direction, I would say. And I guess it will come. So what we are right now focusing at Festo Didactic is if you want to successfully implement a large language model, maybe vision language action, maybe just a large language model to control whatever. What do you have to think about? Now, we said, okay, first question is online versus offline models. And the majority of our customers says, oh, they do not want to have online models. And that's quite clear. Maybe we all use ChatGPT, Gemini on a private basis, but once you use that open models and put company data into the chat, then you are in trouble, because you should not add any internal company data to ChatGPT, or at least not the open one. So if you think about production data, if you think about documentation in your company, I would say offline model is the only chance, or at least to have a contract with Gemini or ChatGPT that you have your closed shop in that situation.
So, this is the number that you have.
Yeah.
Yes.
We talk to a lot of people.
No, you can continue. I think it was a mistake.
Different topic. Okay, no problem. Yeah, so we focus on offline right now. Is it just a chatbot? So that we all know. I would say no, it's not just a chatbot. It's not a solution, because it hasn't. There's no benefit for production or manufacturing, I would say. Support of retrieval augmented generation, yes, that's where we focus on, definitely. So what you do here is you have your query and you say, my production line is not working. Why? What has happened? There's the red lamp over there. Oh, what has happened? Then the traditional large language model has no idea of what that means. But if you provide your manuals, technical documentation, or just text written by some expert, and you provide this as additional information to the large language model, then it's getting interesting. And that's the same as I told you when we spoke about that smart maintenance. That's really the point. Add some specific information about your production line, about your application module, about whatever, to your machine, to your large language model, and then you have some kind like a handbook knowledge. You can ask what is written in the technical documentation. Please help me. I have to replace that spare part. How can I proceed? Maybe you have some troubleshooting. The red lamp. What can I do? And it's also helpful for maintenance. You can every now and then you can add additional documents where you has been faced with an issue. You found a solution. You write this in some kind of a document. You add that to your large language model. And for all your colleagues, this is a benefit. That's definitely what will come in the next years even more. So we did something else. As you can see, it's a local IP address. It's running locally on a computer, which is in a lab of a vocational school. They can ask about what is the machine learning framework, how can I access its stuff, and all that kind of different topics. They can also add their own documents. They can remove our documents. They can play around with that kind of small large language model. And I guess that will definitely change the maintenance part in factory. And of course, function calls. So typically function calls, it means you have your query, but the large language model maybe can't answer it directly. Maybe it has to check the sensors of your system. Maybe it has to check the internet or something like that. And only after that, it can give you a response, for example. So that also means the query might be, or if you combine that, these two ones, query might be, my system is not working. I have a red lamp over here. Please check what's going on. So then the large language model will talk about the context-specific document. It will get the current snapshot of your system, and maybe it can then answer, okay, it was because of this and that. Please remove this part by a spare part or something like that. On the other way around, function calls can also means you initiate an action. So for example, the query is, like you've seen before, put any waste to trash or something like that. And that's what we also did for our robot. So we combined it with a local large language model. You can type your prompt, but you can also record it via micros. It's also working. So what you can see here is we have 2 red work pieces, 2 blue work pieces, and we have a black one over here. And the black one should be moved to trash, and the other one should be sorted by colors. We haven't told the large language model what sorted by colors means. So it makes a plan on its own and decides on its own what sorting by color means. So first of all, the black one goes to trash. We define that green box over there as trash, by the way. So it's okay. It looks like the red ones go to the left box. Unfortunately, as you can see, our cobot is not the fastest one. It is running at 100% speed, but it's not Usain Bolt. And as I said, we haven't prompted the large language model in a way that sorting means the red ones to the left box, the blue ones to the right box. We just said there are 2 boxes. In each box, we have 8 different places for work pieces. And then we just said, okay, sort them by color, and here's what it did. So first move it to trash. Then we have different move operations. And finally, the system says, okay, they are now all sorted by colors. So that's another application scenario for large language models. And I'm pretty sure we will see this in warehouses and logistics with mobile cobots and robots in the near future. And of course, multi-agent systems, that will be the future as well. So not having a huge large language model that can solve everything, but having small specialized ones for special purposes, of course. Yeah, conclusion. I would say AI and machine learning is a fundamental part of intelligent automation and manufacturing right now. Definitely, there's so many application scenarios, in particular if you talk about unplanned downtimes, if you talk about robots, maintenance, smartenance, or how you call it. I also guess that we have a transformation in the human-machine collaboration and interaction. I guess for many tasks, you do not have an expert anymore. You just ask the machine what's going on. You tell the machine what the machine should do. But I also think that education and training are very, very super important, especially to enable people to critically question AI and ML. Please do not forget, even large language models are stochastic systems based on probability, so they do make errors every now and then. And that will be in the future the same. So I would say education is the most important point if we talk about AI right now. Generative AI, large language models or whatever is super cool, super important for manufacturing, but it also has super application scenarios for education. You can create your content automatically. You can go for individualized learning paths. You can use a chatbot like ChatGPT, for example, to train interviews and something like that. You can go for interactive teaching and learning formats. So for me, I like that AI and ML stuff, but I think education is the most important point we should focus on in the next years. Okay, thank you very much. Thanks for listening. Thanks for coming.
Thank you, Tobias. I didn't have the privilege to see your transparencies, but I have been listening very carefully to your words. And also I've been doing my duty in managing the chat on your background, also about different topics. So there is one question coming on the digital twin. So you have been mentioning about productivity and the importance of productivity in the production. So how productive we can really be in terms of planning a production as per our expectation. And there's some ideas about how can we apply the AI on a digital twin. I know that digital twin is basically data-based replication of the reality. So maybe you can bring some of your ideas about that. So first of all, do we have solutions as a digital twin that we can apply an AI, and how can we use a digital twin in terms of productivity of the production processes? Thank you.
My answer is twofold. So on the one hand, if we think about AI right now, digital twin is often used as a high-speed simulation of what might happen in the real world, just to train the AI or the reinforcement model. I guess what will come in the next futures, and Festo, as you know, is also working on the asset administration shell, which is let's say, a digital twin ecosystem, where you have a lot of different data and documents about your cylinders and whatever. And I guess the challenge will be to combine that with interfaces in such a way that can somehow analyze these asset administration shells with AI-based methods. But I would say we are at the very, very first of all, defining what is data which really describes a cylinder. Is it the 3D model? Is it a simulation where it goes back and forth? What about the technical data? What interfaces do we need? What should the AI analyze on that kind of cylinder? So you're totally right. We have to go into that direction. As far as I know, we are, let's say, at the first or maybe second step of that journey.
Okay, thank you, Tobias. So I did promise that I will check the topics of digital twin solutions. There is also this AI for EAC Alliance, and we will check with our partners GIZ and also Zindi to what extent we could really provide these solutions so that could be used on site. Maybe next year, maybe in the coming months, but let's see that. Another point is coming on whether we can leave the recording of these sessions. Yes, we will. I already managed with Paul Kennedy, our partner from Zindi, to share this recording. So not only for you as a kind of repetition, but also for those that they could not necessarily attend, and this will be a second chance for them to deep dive a little bit about informations, and also for me, because I can then see your transparencies on the second round. One more point is that there is a gentleman from Zanzibar here in the call, and he would like to present some AI application on the breast cancer screening project. So of course, this is up to you, Paul, to really take the lead here as a host and let us know if there is room and time for that. Otherwise, there is also still some times left for those of you that would have a question. You can also open up the microphone and put your questions live, if you so feel, or write your comments is also possible. So as you wish.
Dr. Imani, I would say let's see if we can take any other questions on the topic at hand, and if time allows, we have about 9 minutes. But it's possible also Said might be speaking more generally, that he wouldn't be interested in presenting now. I would say let's first see if there are other specific questions, and then maybe we can reach out to Said separately.
there is already one hand raised, Benjamin Mashimba. So please, the stage is yours. Yes. We don't hear you, Benjamin. Yeah. Now, yes. No, we don't hear you. So you did something on your microphone. So you came for a while, but then you just went off. Okay, you can just type it. Yes, please do so. While you are doing this, I can also see here Ndagiwe has put some comments in the chat about sensors. And yes, that's basically the question is, would you recommend students focus more on MLO or feature engineering specifically for high frequency sensor data? Tobias, do you get the question?
Again, please. Sorry.
If you go on the chat, so there is a question on would you recommend students, I mean participants here, on focusing more on MLO or future engineering specifically. Maybe Ndagiwe, maybe you can open up your microphone and put your question more openly. You're welcome.
T-Link operation.
Yes. Ndagiwe. Okay, so
I'm not an expert on that, so
no, I'm missing the MLO. I don't know what MLO stands for. So if I had the idea, then
I would say it's a multi-link operation, which is a Wi-Fi feature that allows to send and receive data simultaneously. I'm not an expert on that, sorry. So I can't answer that question.
Okay. We will try to see if we can come back in a kind of protocol to you. So maybe after the sessions, I would appreciate, Paul, if we can have the list of the comment on the chat sent by email to me, and we will get back to you. Okay.
I see Benjamin shared his question.
So Benjamin, a very last, yes, I wanted to ask if artificial intelligence applications in manufacturing, for example, from Festo, face data scarcity problem and how they solve them.
Yeah, that's a typical problem.
So what would be your say on that?
So what we do at Didactic, of course, we avoid scarcity problems because we have application scenarios where we know there is enough data to come up with a well-trained model. In industry in general, if we focus on the Festo AX part, yes, it's sometimes tricky.
Okay. Yeah, but basically, maybe as a general comment from my side, Benjamin, I mean, artificial intelligence needs data at the end. So we need really to see how to provide the data to the basis in order to make the data analytics. So no data means no data analytics at the end of the day. So it's very important on that. So whatever. So in the education sector, we try to create the scenario so that there are enough data in order to make a data analytics. But in the reality, it's very important to see where those data is taken from. I see one hand raised here, Frank. Maybe you can open up your microphone and put your question, please.
Hello, hello everyone. Can you hear me?
Yes.
Yep.
Okay, my question is on the diagram that you showed on the slide. You showed on the slide for sensor input and internet data input to the LLM. Now, do you do you still use a RAG application like let's say LandGraph to get that data, and then you do that the whatever it happens there, the data from maybe the text PDF, blah blah blah, and then the census data. Like, do you use LangGraph specifically? That's my question.
Thanks for this question. No, not yet. What I use is LangChain. And you're totally right. For that kind of algorithm, I would say LangGraph is it's a better choice. Yeah, so LangChain, it's the code looks like a dirty hack. Yeah, honestly, it looks like a dirty hack. That's an issue of LangChain. If you go for LangGraph, it's more structured. You see more the agents. You see which agent is getting data from sensor, which agent is getting data from function calls or calling an API or whatever. Totally right. If you start from scratch, I would suggest start with LangGraph. I started with LangChain, and now I have some dirty code at that point. Totally right.
Thank you, Tobias. So we are having
just a minute.
Yeah.
Just sorry to interrupt.
Yes,
Actually, even me currently, I'm well versed when it comes to LangChain. So I have that. I'm 50-50 on either switching to LangGraph. Actually, my question was just to know if I'm supposed to to solidify, I should switch to LangGraph. So you mean like I can stick with LangChain and everything can work perfectly, right? Because so far currently I'm well versed with LangChain.
Yeah, so if it's working for you, don't change. Or so if LangChain is fine for you, for me it's fine as well. But if you go more for more structured, or if you let's say assume you're a teacher and you want to explain to students where all the data is going on which edge to which node and so on, then I would say a more clear structured LangGraph code is better than LangChain. But if it fits for you, don't change it.
Yeah.
I also know that LangGraph is better, but I don't change my code right now. It's working.
So it seems that your answer was satisfying, Frank, with the thumb up. So we are having 1 minute, and I would like to address to the last question from Lightshine. So a nice name, Lightshine. What comprehensive strategy do you propose to accelerate the integration of artificial intelligence across the EAC community, considering the region's current technological gap? Maybe if you allow me, Tobias, I would like to address this question.
Please.
First of all, as Tobias was mentioning, education. So that's a mother of everything. So education is so important. And that's also the reason why we are here. We would like to collaborate with Zindi. We would like to collaborate with GIZ and also AI Alliance for EAC. So to make sure that knowledge will develop, but then it comes to the application. Second part of the strategy is really to work with the private sectors. So there are already private sectors, very advanced one. For example, I know that the company Kronos is one of the leading company of the world, at the world levels, that is having the entire support centers for EAC based in Kenya, and it's very important to see to what extent AI application could be used with these world leading companies. But there are so many others. So the private sector is already on the edge of industrializations and on the smart manufacturing. So it's very important to connect education and the private sector and industry together, so that those application or those skills development and knowledge would be immediately applied in the private sectors. And of course, there are also ideas of partnership with development agencies. We will continue, as I understand. This webinar is just very much the very early step towards disseminations of AI in the manufacturing. We will continue on that. So there are already discussions how we can be part of this alliance, and also how can Festo really support industrialization in this beautiful continent. For sure is important, because Festo is industry, and Festo exists because industry exists. So if there's no industry available in the economy, it will be no future for the company Festo as well. So this is a very natural relationship that you're having with you guys. in order to disseminate the advanced technology and of course smart manufacturing for the future. So that's in a nutshell our strategy for the coming years, basically. Yeah. Thank you so much. So yeah, we have just overdue the time by 2 minutes, Paul. So I would like to hand over to you as a host and maybe take it from there. Thank you so much.
So I've muted myself. Thank you so much, Dr. Imani. Thank you so much, Dr. Schubert. It's been a great session. Great to hear about the work that Festo is doing and shed some light on some of the applications of AI in manufacturing. And lastly, I'd like to thank all the attendees. We will certainly make the recording available. And I'd like to remind everybody, if you haven't yet, to make sure that you are signed up at zindi.com, zindi.africa/AI for EAC. The link is in the chat. That's how you can follow all the other webinars. That's how you can know what's coming up when we release practice challenges, as well as the final challenges of the session. We appreciate all of your time today, and we will leave it there. Thank you, and good evening.
Thank you very much. Good evening. Thanks for the opportunity. Have a nice day.
Thank you.